CPU operations using registers. In this part, we will learn a little more details inside CPU. Look, we just use one simple operation, addition, to show you how to, implement the whole operation in detail. Yeah. All right, so let's look at that. When we start, let's look at the internal storage types in CPU. Yeah. We need to store data, right, inside CPU. Yeah. Here with the background from cache memory. So remember the top of the pyramid. So we have a pyramid hierarchy. Yeah. On the very top. Yeah. At that time we use registers, right? Yeah. Here, if we go back to the history a little bit, the internal storage, three major choices. The first one, a stack. Stack, very old time, at the early time of CPU, using stack to store data. Yeah. And accumulator, also another way, accumulator also store data temporarily for execution, for instruction execution. Yeah. So these two types used in old CPUs, very early time CPU. Later, a set of registers, and then also now, the current time, we use registers. Yeah. All right. So you can see in our module 3, the pyramid, top of the pyramid, we use registers. Because the current CPU, we all use registers. Yeah. We never need to use stack accumulator. Yeah, but here, in this part, I want to explain using stack way, accumulator way for the comparison purpose. So you can see the register way much better than the old way. Yeah. All right. First aspect of comparison, explicit and implicit operands. Yeah. Operands, when you do operations, the data, that's the operand part. There are two types of operands. Explicit, you can see, this is the operand. Implicit, you cannot see. In the instruction, you do not see the operand appears anywhere. You do not see any place there is an operand, but hidden somewhere, some hidden place, there is an operand. Yeah. All right. Stack. So let's look at stack first. For the stack, operands implicitly on the top of the stack. So we know the stack data structure, right? Yeah. First in, last out. Yeah. Push, pop, right? Yeah. Yeah. Here, let me use a simple instruction to show how to use stack to do a simple operation. Yeah. So let's look at this example. C equals A plus B, 3 variables, A, B, C variables, and the data for A, B, C variables all come from memory. Okay, memory. Yeah. All right, so let's look at this, step by step, how to do the operation using stack inside CPU. Yeah. At the beginning, the stack is empty. Yeah. All right, then we do the first step. Push A, the instruction. Yeah. We call push A. Yeah. When you see this instruction, you do this. Retrieve data from memory address A. Yeah. A. So what do you mean A, right? It corresponds to a memory address. we use A to represent it. Yeah. All right. And push it into the stack. After you load it, you push it into stack. So you get an item. Here I use little a. Okay. That capital A, that's the address representation. Little a, so that's our operand representation in the stack. That's step 1. Then step 2, push B. We need to load data B from main memory through memory address B. Then we push it into the stack, on top of the stack. You can see, yeah, that's step 2. Step 3, now this is the step 3, add. Instruction, you only see add, ADD. You do not see the operands, right? Here you can see hidden operands. Add operation, we need 2 operands, right? A and B, but we do not need to specify these 2 because they are in the stack. We just pop 2 operands, 2 numbers, the top 2 numbers in the stack. So we do not need to specify anything. Yeah. So that's the implicit operands. Add, okay? Yeah. Add them and push it into stack. After the addition, you get operation, you get a result, right? That result, we push it into the stack as the C item, little C item. Yeah. But we did these 2 things before we push. Yeah. Pop B on top, right? Pop B to the ALU device. So what's the ALU device? Here, I didn't draw ALU device. A, arithmetic, L, logic, unit. ALU means arithmetic logic unit. ALU device. When we do computation, we need a special device to do it. Okay, so we call it ALU device. Arithmetic logic unit. ALU device. Yeah. Okay. Pop A to the ALU device. Then you do addition inside ALU device. Then push it back as C item. Okay. All right. So then the last step. After that, you get the answer. Last step. Pop C. So you save the value of the addition result back to main memory at address capital C. Yeah. Okay. So the step 4, store data to memory address C. So you complete the whole operation in these 4 steps as the detail. Okay. Yeah. So look at this kind of detail. Yeah. So that's what happened inside CPU. Yeah. But old CPU. Yeah. So later we will see, recent CPUs using registers to do the same thing. Yeah. All right. So that's for the stack. Okay. Next, accumulator. Yeah. 1 operand implicit from the accumulator. 1 implicit, 1 explicit. Okay. So here you can see both implicit, right? Both implicit, hidden, both. Yeah. Here, 1 hidden, 1 explicit. Explicit. 1 hidden, 1 visible. Yeah. So that's for the accumulator. We will see that next slide. Yeah. Then registers. Only explicit operands. Yeah. Both explicit. Both explicit. Okay? Yeah. So we will see also next. Yeah. All right. Next slide. So let's look at accumulator way. Yeah. So this time with the, experience from the stack. So this one should be pretty easy for us. At the beginning, the AC accumulator empty. right? Yeah. Then first load A and store it in AC. Yeah. Store it. Load from memory address capital A and store it in AC. All right, so you get one operand there. Yeah. Second step, add B directly. Okay, add B. When you do add B instruction, this is visible. This operand is visible, right? You see that B. Yeah, that corresponds to data in memory. Yeah. So you retrieve data from memory address B, then you add A hidden. Yeah, A operand, little a operand hidden inside AC. So you take it, you add it to the B value, then you get a result, you store it as C value, little c value in AC. So that's step 2. Okay. Step 3, you store the little c value in the address capital C. So then you complete the operation. So you can see in this way, you just need 3 steps. In the previous stack way, you need 4 steps. Okay, yeah. So you can see the difference. Yeah. Yeah. So that's the difference. Yeah. Next one. Yeah. For the register way, we have 2 different implementations. Here, the first one called register-memory type architecture way. Yeah. Why we call this name? Later you will see there is a reason we call this name. Yeah. All right, so let's look at the same operation, our implementation. Yeah. At the beginning, yeah, here, R1, R2, R3, so we have multiple registers. Yeah. Here, we put 3 different registers. We just use as we need. Yeah. All right. The step 1, load R1 from memory address A. Yeah. Memory address A, after you retrieve it, you need to store it in some specific location in the registers. Usually in the CPU, there are several. There are, certain number of registers you can choose. Yeah. Yeah. That number later we will see 32. 32. That's the number. So in your mind, so you can imagine. So that number. Yeah. Here we use R1 to store our first operand A, little a there. Yeah. Then step 2, this time we need to do addition. The addition, 2 operands. These are the 2 operands. The first one, R1, so we take the value from register R1. The second one from memory location B. The result stored in the register location R3. Yeah. So that's the meaning. You can see we have the result in R3. So the last step, we store the value from R3 back to the memory location capital C. And we complete the whole operation. Okay? Yeah. Now I can explain why we call this architecture register-memory architecture. Look at our main operation. This addition is our main operation. Okay? Look at our ADD main operation. You can see the first operand comes from the register. Second operand comes from memory. So that's why, based on this property, we call it register-memory architecture. Okay? All right. Next, similar, but this time register architecture. So you know the meaning. Yeah. So let's implement this same operation, but here slightly different. Yeah. Yeah, look at this addition this time. Pretty similar, but some difference. Yeah. All right. Step 1, load R1 from memory address A, the same as before. Okay. Yeah. Step 2. Oh, yeah. Step 2, still, we do the similar thing. So I still use this location. Load data from memory address B, store it in R2. Okay, 2 load operations before we do the addition. Step 3, then both operand values come from register R1, R2. Result, we store it in R3. The last step, store value in R3 to the memory address capital C. Yeah. So that's the whole thing. Yeah. So look at this. So you can compare this way and the previous way. Pretty close, but there is some significant difference. Okay. The main difference is here, the operands locations, both from registers. So we call register architecture. 2 different architectures. In our next video, we will compare these 2 architectures, advantages and disadvantages, so that we can understand better. Yeah. Here, I can tell you the conclusion first. The result, this architecture is better. This architecture is better than the previous one. So later, the RISC architecture, yeah. So we talk about the RISC. RISC architecture used this way because its overall performance is faster. Why? In our 3rd video, B.3, we will discuss that. And later, more places, we will see the comparison, difference, more discussion. All right, so let's finish our B.2.